So the final speaker of the session is Jinfeng Xiao, and he's a second-year postdoc from the University of Illinois, and this is his second participation and his first individual win of a Dream Challenge. Congratulations.
Thank you. Hello. In fact, I'm not second-year postdoc. I'm second-year PhD student, but it doesn't really matter. And so I'm very glad to here to present my work together with my advisor, Dr. Jinfeng. He's not here today, but he will be here with us tomorrow. And about a novel method to predict ALS progression. Basically, it's a kind of a modification of random forest method, but we add something to rank features and to predict ALS progression. And the title looks a little bit long, but it basically says everything I want to include. So the goal is to select important features and predict ALS progression. And the way we select important features is to use weights to aggregate weights along patient's paths across the random forest. And I will go into more details later. So, as it has been introduced by the organizers and many speakers, the prediction on ALS progression is very important because it may shed light on the disease treatment and people's understanding of biology. And the goal is to predict progression and find out the important clinical variables. The progression rate defined by the ALSFRS scores ranges from 0 to 40. Okay, here comes to some of my special parts that hasn't been mentioned before. It's sub-challenge 3. The data is not from PROACT. It's from 2 national registries. One is the Irish National ALS Register, and another one is from Italy. So the number of patients is smaller, much smaller than the sub-challenge 1. There are only 450 patients available for training. I don't know how much you use for testing. So. And there are up to 68 clinical variables available in this data set. And for all the data, all the training data, we know there's data from 0 to 3rd month. And we also know the training data status from 3rd to 12th months, but we pretend we don't know that so that we can make some predictions. And one thing special about this challenge, compared to another challenge I won, that is the Persist Cancer Challenge. One thing special with this challenge is the strict rule on the number of variables we can use. And here I would like to make a distinction between 2 concepts I will be using throughout this talk. When I'm saying variables, I mean the variables provided in the original data sets. And when I say features, I mean those features encoded from those variables that I feed into my machine learning algorithm. Okay, so let's first make this clear. And when a new patient come in all those the 68 available clinical variables, we are only allowed to select 6 of them plus 1 cluster number. And not every patient has that many variables available, of course, but we need to select 6. And then we make prediction only based on those 6 and that cluster number. So that's why my advisor and I got very interested in this challenge. That's a very important reason, because at that time we had an idea in mind to select the important features with some new way, and we feel like this is a quite good chance to test it out, and it also may have a great impact on the medical science. So we did that. And as I said before, the evaluation of the challenge is the aggregated least score of concordance index, Pearson correlation, and root mean square deviation. And the data released by the challenge organizers are their sums, but I'm using their averages in this presentation. They're basically the same. Okay, so here comes the most interesting part. I would first give an outline about my approach and then go into some details step by step. So Before approaching the data, we need to process them first, and there are, of course, some data processing. We need to drop some features, and we need to do some imputation, and we also need to encode some of the variables into features to feed into our algorithm. And after dealing with all the data, now we are ready to train the model. So basically, it's random forest based, and we first get a big random forest for all of the patients, and then we throw the patients, for each patient, we throw them through the random forest and keep track of their paths along the trees. And I will introduce what I mean quite soon. And based on the path, we can assign a weight to each of the patients and each of the features and each of the variables. So based on those weights, we can apply some clustering in the weight space. And locally, we have preliminary results showing that the clustering based on the weight space can give much better results than the clustering based on the value, feature value space directly. And after we have did clustering, we have done clustering with all the patients, and we now train a new random forest based on each cluster, because each cluster has different list of important features. And so we get a new set of random forests, each corresponding to each cluster. And now, when a new unknown patient come in, we first decide which cluster we need to use. And we do that by finding its nearest neighbor inside the weight space. And the cluster of that nearest neighbor is the cluster that we are going to use. And then we just use that random forest to do the prediction. So here comes the details about data processing. The most important part of data processing is how to encode clinical variables into features. And first, we discarded any variables with missing rate higher than half. And we also tried discarding of those only with missing rate higher than 80%. We tried that, but the local result does not differ much, so we keep with that. And for the features to the variables to features conversion, there are 3 different types of variables that are shared between subchallenge 1 and 3, and there's a specific kind of variable that is specific to subchallenge 3. So the first 3 kind of shared variables are, where's the laser pointer? Okay, here. So the first 3 shared are static categorical variables with n levels, static continuous variables, and longitudinal variables. For static variables, I mean there's either only one measurement or there are several measurements that are taken very, very close to each other and it's supposed to be the same value. So for those kind of binary static variables, we encode that into n+1 binary features. You may wonder why there is a +1. Of course, the n here indicates the number of levels, but the +1 is the missing indicator. So if that variable is missing, we set true to this one binary feature and 0 to all the else. And for the static continuous variable, it's straightforward. We just pick out its value as the value of the feature. The most tricky part is the longitudinal variables, which is kind of a time series. You measure the same variable at different time positions, and because the number of variables you need to feed into the machine learning algorithm should be fixed, excuse me, and should not change much between from patient to patient. So we encoded all the longitudinal variables to 3 continuous features, which is on the next slide. And the one special variable from our subchallenge 3 is the stratification, because they are from 2 national registries, so we add 1 binary feature to indicate whether the patient is Irish or Italian. And finally, the missing values are simply fed in by a very, very large number. We do that to ensure that every missing value go to the same direction in the random forest. So basically, we did not fill in the missing values. We just tell the program that the value is missing, both for the categorical variables or the continuous variables. And here is an example of our encoding of the longitudinal variable into certain features. For example, suppose we have an imaginable variable whose values are in the first column, measured at the time point of the second column. Then we take 7 statistics of the feature value, the mean, number of records, first, last, max, mean, and standard deviation. And we also take 2 statistics from the time value. And apart from that, we calculate the rate of change between 2 consecutive records. So it's, for example, for the first 2 rows is 2 minus 1 divided by 2 minus 1. So we generate a sequence based on the rate of change, and then we calculate some of the statistics based on that sequence. The reason why we use so much statistics is from the challenge held 3 years ago. The winning team at that time did something so complicated, so we just learned from them. Okay, so now the data is ready, and let's go to the model, and here are some mathematics coming in. I like to define that very precisely. So there are several steps for building the model. First is initial train. We train random forest denoted as F with NT trees, number of trees, and NP is number of patients, NF number of features, and NV, we say it is a number of variables. And then we track the paths of patients in each tree, and denotes the path of the P's patient in the T's tree as PPT. And the information contained in PPT is the order of node you visit when you drop that patient inside a tree. And the intuition here is that the first node you visit should be the most important variable for that patient, and the second node you visit should be more important than all the else. And based on that, we assign a weight to each of those to each feature, each patient, and in each tree, and we record and we record the weights of those information inside a 3-dimensional matrix whose size is number of patients times number of features times number of trees, and each entry is defined by the maximum value of 7 minus location of that feature in that tree, and 0. So basically, it means if one feature appears at the first node inside one path, its weight is 6. And if it appears at the second node of one path, its weight is 5, and so on. We only count the first 6 entries, so the first 6 nodes within each path. And this formula, we can fine-tune that to make the model more fit, but we didn't do that due to time limit. But it's absolutely one thing to do. And after finding out those, we marginalize over all the trees to get the features, to get the weight of each feature of each patient. So you kind of compress the 3-dimensional matrix to a 2-dimensional one. The matrix V records the weight of features. And after you do that, recall that each feature is encoded from some variables, and we are required to select 6 variables, 6 original variables instead of 6 features. So we need to aggregate those weights of features into the weights of original clinical variables. And there are several ways to do that, and we find the best way in our local testing is to take the mean value of all of the weights encoded by, so suppose we have a longitudinal variable which encodes for 13 features, and we take out all those 13 weights of the 13 features and take their average value as the weight of that clinical variable. And then we get a 2-dimensional matrix which can be regarded as a point, which each row can be regarded as a point in the NV dimensional space. And then we do the clustering inside the NV dimensional space. It's k-matrix clustering. And then within each cluster, we calculate the total weight of each feature. So we sum over all the patients inside that cluster to get a weight list for all the features within each cluster. And then we just take the 6 greatest values of that aggregate weight as our selected features and use that features to, and use those 6 features to train a new random forest to represent that cluster. So after we have done with all the cluster training, we are ready to predict new patient survival. And when a new patient comes in, first, we find out his cluster number by calculating the, well, if you recall, the U matrix is the aggregate weights of clinical variables. And imagine that when a new patient comes in, it is an additional row of that matrix. And you calculate following the exact pipeline, and then you can get the weight of that, you can get the position of that new patient in your weight space. And then you find its nearest neighbor in the weight space as the cluster number, and you just do selector and predictor following the cluster information. So that's all we did, and let's see the results of our study. So we set the cluster number to 6, and it turns out that 5 of the clusters have exactly the same feature listing. And cluster 1 to 5 differ from cluster 6, but they share something different, something in common, because swallowing is a subset of mouse. So that also highlights the importance of the mouse functioning in the prediction of ALS progression. And here's the performance of the top 5 teams of subchannel 3. Because the origin of the y-axis is not there, so it's kind of aggregated. But the point here is that the difference between our team and the second is much greater than the difference between the following teams. And the likely ratio that we overperform the second team is quite high. And we also did some local testing with some other methods for ranking features. For example, there's a package available in R called Random Forest, and they offer an importance function that gives you a list of the importance of the functions. And they do that by permuting the nodes in the random forest and see the result. And it is only preliminary result, but our method overperformed the random forest package by 30%. And and I said just now that our clustering is based on the weight space, not on the value space. Value space, I mean, each coordinate is the exact value of that feature instead of that weight. If we do the clustering in the value space instead of the weight space, the result is shown in gray, and it's about 40% worse than our current method. So that's the inspiration we get for submitting this kind of method to the challenge. And I'm quite excited about the result. And finally, I would like to thank my advisor, Jinfeng, for all his inspiring ideas. And that's all of my talk, and I'm ready to take in any questions. Thank you.
So is there any guarantee in the random forest that the depth of the node, which is what you used for the weight, it was 7 minus the depth of that node, that the depth of the node is actually more important nodes are guaranteed to appear higher? Because you can imagine alternative trees in which the order of the nodes is sort of reversed, and you get the same, more or less the same decision tree. So what kind of guarantees are there statistically in a random forest that more important nodes will appear higher? And how is there any way to, any variation in the random forest algorithm that can enforce that criterion, which would then make your method perform even better, I think?
I think random forest choose the node so that the node impurity will decrease the most after each judgment. So you choose that variable because that will decrease node impurity. Maybe you can measure it by the mean squared error or something. It splits the data best into 2 groups that, well, you can say that the link between a node on the top means that after it separates the data into 2, the similarity between the 2 sets of data are smaller than the similarity within the group of data. So that's the intuition we have for choosing that kind of weight. Does it answer your question?